All right, higher level students, we're going to talk about something called gravitational potential in this video. This will lead into a discussion of something called the gravitational potential gradient, equipotential surfaces, and we will end talking about escape velocity in a couple of videos from now, okay? All right, so just to remind you guys about gravitational fields, remember how gravitational fields work, like the gravitational field of the Earth, okay? We define the gravitational field strength as being little g. This was also the acceleration due to gravity, as we saw. And we defined it as the force per unit mass acting on a small mass, usually called m naught, a test or point mass, placed in the field, and the SI units were newtons per kilogram. The field strength at a distance r from a point mass m on m naught, okay, was given by Newton's law of universal gravitation. What we did was we divided that by m naught, and we got this very nifty expression for little g being big G times the mass of the Earth divided by the distance away from it squared, okay? R is not necessarily the radius, it is a distance, all right? And we saw that the gravitational field strength and the gravitational acceleration are indeed the same thing, and that was one of those like, oh my God, aha, awesome, wow moments in physics, okay? Also remember what the shape of the weight against distance looks like, both inside and outside of the Earth. Inside it's linear, outside it falls off as 1 over the distance squared. The farther you get from the thing creating the force field itself decreases, okay? All right, and this can easily be imagined again by looking at the vector field lines. The closer the field lines are together, the stronger the field. And we said that, okay, so in the case of the Earth or any other object that has a lot of mass, you're going to have the greatest weight on the surface of the Earth, and you're going to have less weight both inside and outside of the atmosphere, according to this graph right here. And don't forget the simplifying assumption that the field lines as they hit the surface of the Earth are perpendicular. They're really not, because the Earth is curved, okay? All right, now also don't forget that at the surface of the body, r is exactly the radius of the body. At the surface of a body, g is also at its maximum value, okay? All right, now as you get farther from the thing creating the field, the force field decreases not only inversely, but inversely squared, okay? That's Newton's law of universal gravitation. And I have here a great TOK question for you guys, okay? Now, we talk about how at great distances from the Earth, that the strength of the gravitational field goes to 0, it becomes negligible. And a good TOK question would be, how do scientists decide when an effect is so small that it can be negligible or ignored? It's interesting. And I think there really probably is no definite answer for this. It depends on the application of what you're trying to do, whether or not you think it's negligible or not, okay? You know, I mean, every place in the universe experiences an effect from Earth's gravitational field, okay? Whether that's negligible or not, it depends on what you're trying to find out, or how sensitive your equipment is, okay? All right, now I have to redefine gravitational potential energy, and we're going to do that right now, and you'll see why this is in just a second, okay? Remember how we defined gravitational potential energy? We said that it was the mass times g times the distance above the Earth, where the Earth was taken to be a height of 0, okay? And we said that the gravitational potential energy is the energy needed to move a ball, for example, in this case a basketball, against the gravitational force between the Earth and the ball, or the ball's weight, okay? As the ball comes down to Earth, its GPE decreases, but its kinetic energy goes up by conservation of energy, okay? And we said that, therefore, the gravitational potential energy is proportional to the distance away from the Earth, and in fact, we found exactly that GPE was mg delta h, okay? Again, conservation of energy argument here, okay? Also remember that work is force times the distance, all right? And the work done by the force of gravity on an object and bringing it a distance delta h towards the center of the Earth is just given by mgha minus mghb, which is gpea minus gpeb. That is the work done, even though remember that energy and work are not the same thing. We measure them both in joules, okay? Very important for you to remember. Now, the problem, as we discovered last time, as we go away from the surface of the Earth, the acceleration due to gravity on any mass ends up decreasing. Therefore, we cannot use mg delta h anymore because g is now a variable, okay? What to do? Okay, well, there's an easy solution. To avoid it, what we do is we use our new expression for G and plug it into our GPE equation. So it becomes mg delta H, or mgm over r squared times r, where delta H is now just the distance r. And I get that my now universal expression for gravitational potential energy is G times m over r, and that works everywhere, even on the surface of the Earth. Okay, we have therefore figured out a way to avoid the problem of G getting smaller as you get further away from the surface of the Earth. It works. Now, usually we take 0 GPE to be a point at infinite distance from the Earth. Now, why would that be? Not the Earth's surface with the above equation. Because 0 GPE is the place where this expression goes to 0. It's going to be when r is infinite because r is on the bottom of this fraction. Okay? Turns out that we still need to maintain the fact that an object's GPE, as we approach the surface of the Earth, has to get lower, okay, has to decrease. Now, the only way that's going to happen, and by defining it to be 0 at infinity, is to make the energy negative as it approaches the surface of the Earth, okay? So, therefore, the GPE near the Earth's surface must be negative because it has to decrease from 0. As before. And as before, GPE is the total force applied on a mass through a distance to bring it to a certain point. Therefore, GPE is negative. There's a negative sign there, GMM over R. I'm going to prove this mathematically very shortly for you. Okay, but you see conceptually where that negative sign has to come from. Now, I've made some graphs here just to show you a comparison of 3 different ways of thinking about gravitational potential energy. The first is taking mg delta H, okay, without considering the fact that G changes. This is wrong and boring because it's a straight line. That's not a very good straight line that I drew, but you get the idea. It's a straight line going through the origin. That is not correct. That is wrong, okay? Next one, taking GPE as GMM over R, we get an inverse relationship, not inverse squared, but an inverse relationship right here. This is wrong, okay? This one is right. This is what the gravitational potential energy of something looks like at a certain height from the Earth, okay? It's negative, and the shape of the function is this. It is a negative inverse relationship, okay? Remember the shape of that graph. This will be a really important shape, a graph that we will deal with later. Okay? All right. Okay. Another way to think about it. GPE is the total work done on a mass to bring it from infinity to a certain point. Now, as usual, work is the area between a force displacement graph and the x-axis. Now, we've talked a little bit in class about calculus. We'll do this again if you guys need it. Turns out that if we integrate force over a distance from infinity to r, we end up using the rules of calculus and integrals that the work done is negative GMM over R. Remember, the work done is equal to the gravitational potential energy. This is the expression we got before for the gravitational potential energy, and this explains mathematically where that negative sign comes from. That's awesome. We love calculus. It's our friend, okay? And R is the distance from the center to the center of the mass it is being brought to. So in other words, this work, you can think of the work as being stored in the field as gravitational potential energy, as always, and it's exactly equal to the gravitational potential energy. That is why work is in joules and potential energy is also in joules.